I go down a level in the next item. The question of what exactly I should supposed to be was answered in the discussion.
I don't remember what it said.
I was the one that asked it. Okay. And that's what I took it to be. So I thought it was saying if this question mark ends up with a positive, then make that feature the majority feature among all of the positive examples in the entire data set. And if it's a negative, then set it to be the majority feature of all the negative examples in the data set.
So that is the third one where that's the third.
No, the third one is just ignore it and treat a question mark as its own feature.
I took that to mean I take all of them to be one and the question mark to be the other.
Wait,
So I discretized it. I said this question mark is one value and all the labels get treated one way, and then everything else turns into a bucket that handles all the others.
Oh, yeah, I didn't do that. I used the question mark as though it represented. It's a weird mushroom rather than.
I actually loaded it that way too. I actually did a missing feature, and I said anything with this, not just this one, any missing one, turn that into its own thing.
Yeah.
That was an interpretation that I would think was too weird, but.
All right, let's get started, folks. We have a.
Okay.
We definitely have a day today. How's everyone?
Yeah.
Okay. Announcements. Some of you might be aware of this. There's a homework due today.
Yeah.
If you've not started, now might be a good time.
It's so much easier to stick through and debug.
Which
one? Pie charts.
Oh, the homework.
That's free.
Yeah. I don't remember which one I'm using. It's way too much info.
Of course, there's the standard rate policy, which is you are allowed to turn it in on Wednesday, tomorrow midnight, if you're willing to give up 10% of whatever you ready, right? That's the late policy for the class, and that's the late policy for the homework. Any other questions? I know that there were a ton of questions about homeworks on the discussion board. It's nice to see the discussion board so active. It means that at least some of you are active. Are there any questions that you'd like to bring up? Yes.
So in the setting B data, I did not get 100% accuracy when I trained on the training data and then tested on the training data. And
For what depth?
With no depth limit. And so I assumed that must be wrong, but talking to some other people, they said they got something.
Interesting. I'm surprised at that. I did believe that the data set was consistent. Do you guys know about that?
I'm getting the same thing, but it's on an extremely small amount of numbers, so I figure at some
It's possible that there was some noise in the data.
Yeah.
I mean, it's definitely true that there is noise in the data. It's possible that there might be some inconsistency in the data because we basically created this setting B data by taking the original data and adding noise. And by creating random perturbations, we might have actually had two examples with same example with different labels, and that would account for this observation. If you do observe it, mention that in your report. Give some statistics. Tell us how many such, what fraction of training examples that happens, and hypothesize what happens, why you think that might be the case. If you can find examples that are identical with different labels, discover them, and that's the point of the report really, where you mention these kinds of interesting observations. Yes, you've had your hand up for a while.
I was just going to say, I guess I could have, my evaluation could run, but I did get for the training B, I was able to get like 100% with the training. I had a much larger area on the test data, but on the training I was able to.
Okay, here's the fun thing about this kind of a data-driven experiment. The data is what it is. You make your observations and you tell us what you see. Now, what is interesting is that what you said and what you said, clearly only one of them can be right. Right? I do not off the top of my head know which one is right, so I cannot really comment on that. But you must be, so one way of doing like getting sanity checks on the decision tree algorithm is exactly what you guys did. Will you get zero training error on the training set across zero or close to zero training error across all the settings? If you don't, you must be able to explain it. And you want to take that? And the only way you can kind of account for that is to, if there are examples that, if the data itself is inconsistent. So you should be able to prove it by either finding that certificate, that one example or two examples where the label is mismatched. If no such situation happens, then there might be a bug.
Okay, but it should be able to get 100% accuracy on the training data always, unless the data is inconsistent.
Yes, if you allow infinite depth.
Okay.
Yes.
How much explanation are we expected to give on, say, for instance, the linear classifier portion? So I can just write down like values and say these values came to me by hand of God, but that seems like it might not be appropriate.
So
how
if you
much
can make any
explain-
reasonable guesses as to what the function might be,
Okay.
in a Boolean sense,
Okay.
that would be useful. The reason is, if say your function that came by hand of God or something was wrong, and it so happened that your explanation was okay, you might get partial credit. Other questions? Yes.
For the linear classifier, we can assume a function and then try to find the weights and the bias for that function, what we think is correct.
But you are assuming a function, right? It's a linear function. You're assuming that the function is a linear threshold unit and discovering their weights. One of the reasons why I have this question, before you've seen any training algorithms for linear classifiers, is to force yourself to discover linear classifiers and kind of convince yourself that in certain cases it's actually ridiculously easy. In certain cases it's not, which is kind of the reason why we have this whole family of linear classifier algorithms. But in all cases you do assume that the function is a linear threshold unit and you have to find the weights and the bias. In some sense, if you think about it, all I'm asking you, that seems like an understatement, but what I'm asking you is the weights and the bias. Because we agreed in the question that the function is a linear threshold unit. I saw another hand up. Yes?
So when we're writing our report, do you want us to say, well, here's setting A, question 1, and the answer for it? Or just like say, well, here's what we did for setting A and do a big blob of all of the questions?
Let's see. Can you remind me what was question 1 and question 2?
So question 1 is something like describe what you did, and then question 2 is report this number. Question 3 is report that
can you just,
number.
to make the lives of people who are grading easier, just separate it out?
Okay.
It might be like just one sentence or maybe just a word.
Yeah.
Just make our lives easier, please.
Okay.
Yes.
On setting C, where we want to find the missing features, when should we try to find a major feature? Just on the input data or where we reach to a subset?
Oh, it's not a subset, right? Think about it as a, okay, technically speaking, this question is underspecified. It gives you the freedom of choice to, play with this. So, whichever option you pick, write about it. There are fewer wrong answers than you would think. But if I had to do it, I would pick it on the subset. Or maybe on the entire data. Both of them seem reasonable. So I would try them both. And in fact, the way I would actually go ahead with this is, if I had to do this, is to try out both and look at cross-validation and see which is better, and that is the answer. The question is deliberately underspecified because you have to make decisions as you go along. Anytime you apply a learning algorithm in real life, you are faced with these kinds of questions. And you have to come up with reasonable ways of guesstimating that thing. And one reasonable way of doing this is cross-validation. Another one is to say, I know the data. I know the domain, here's the right thing to do. Justify your choice either way. Either one is okay, but you need to justify the choice, and that's the point of the report. And in fact, you will see that in if you read papers where these kinds of things are applied, you will see multiple papers where some of them make a choice, another one makes the other choice, and both might be okay. Are there other questions? There were a bunch of questions about Kate machines. Have people been having trouble accessing the Kate machine? Has anyone had trouble accessing the Kate machine? Jay just posted a note on Canvas, a FAQ sort of a thing with Kate's own tutorials on how you might ship your files to the Kate machines for running your tests. If you feel that is too complicated, I found out just yesterday from Max that the Kate lab is upstairs. Kate lab is right there. If you so you could even do you could walk over and use your USB stick or something. And I've heard the transfer rates are faster with that. So do try to run your code on the Kate machines at least once before submitting, because that's where we will be running your code, and I do not want my TAs to be debugging your code because of obvious reasons. So do try to run it on the Kate machines. If it so happens that you are unable to run it on Kate machines at all, and yet somehow magically it works on your laptop or your desktop, that means that something funny is going on in your environment. You might have assumed some environment variables, or you might have some dependencies installed that are not on the Kate machines, which makes it impossible for us to grade. Once again, help us help you by simplifying things. So try to run it on the Kate machines before you submit it. Any questions about that? Yes.
So I have a large library of functions that I use for homework and for research and stuff like that. Just to make things easier, should I just break off only what I use? Okay, all right, gotcha.
And you should not be using any machine learning libraries.
Naturally, yeah.
There was another thing. A bunch of people also had questions about the cross-validation because you were not able to trust the results that you got. Because your decision trees had a certain shape that you thought, oh, that can't be right. And there was a discussion on Canvas as well. And how many people feel that your answer cannot be right because your decision trees are too small or too large? The best decision trees. How many people are shy and won't raise their hands? Okay, at least one person. Are you raising your hand, or do you want to?
I was going to say, I was very surprised to see that my best decision tree had a depth of 2. And I was like, I accepted it, and I'm okay with it because I want to get it done. But I was surprised to see that.
I heard multiple people talk about this, so I just thought I should address it. That's right, actually. I mean, the best decision tree comes up with a depth 2 or 3, or depending on how your random, depending on some initialization or something, I'm not sure what. It so happens that on this data set, the best trees seem to be short. But the cross-validation still asks you to report numbers for rather big trees, but you don't even get those big trees. And that seems like a bit of a letdown, right? Why do you have to run all those experiments when it does not even grow that big? But the point is, how do you know up front, without actually doing that experiment, how do you know up front that the best decision tree is not depth 22? Yes?
On that note, can we simplify it and just say all remaining tests had the same result, or do we actually have to explicitly write out?
Could you actually do write out?
Okay.
Because it will be, since really in the process of this conversation, you and I and you have given away an answer. So I would like to actually see the result, rather than just the statement.
Okay.
But in fact, you could even plot a graph if you want, and that might make your life simpler. Remember that you have a page limit of 10, and every extra page beyond that will lose you a point. And this was a lesson I learned from when I was a student, when I used to write volumes of text, and my TAs hated me. So again, make our life simpler as well. But the thing is, it's not surprising that the best hyperparameters might be very small or very large or something, but the important thing is you do not know that upfront. And when you see a real data set out in the wild, how do you know? Unless you try. So let's just, that's again, the point of the homeworks is mostly to give you experience with what kind of a sandbox experience with what real life data challenges you might face. So you never know what the best hyperparameter might be, so you have to actually try them on. You never know what choices you might have to make, so you might have to try them on. And all these things will only, and as you go along in the class, you will have to endure other such choices in your homeworks. So that's announcement number 1, and wow, that's a long announcement. The other thing I wanted to discuss was the TA office hours. We used to have office hours on Friday, and by popular request or by some kind of a request, we moved it this week to Monday. This was JS office hours, and it seems to me that this might be generally a good idea. Just a quick show of hands. How many people would be okay if we moved the Friday office hours to Monday, knowing that most of our homeworks are due on Tuesdays?
Would there still be another TA hours and just the one on Monday, or would there be
There'll be 2 on Monday. Did you have a question? So I'm considering making this a permanent move. It also works well because it seems like Friday 4:30 the campus is deserted. That said, if you actually feel that you would like office hours on Friday rather than Monday, please send us an email. Send me an email if you want it to be private, I don't mind. Because I don't want to, if you've made any plans around these office hours, I don't want to ruin it. So please send me an email. If barring any emails that I get, say, by Friday, we will have this move will be permanent. We'll have 2 office hours on Monday and none on Friday. Third announcement, given that you like your homework so much, there's going to be another one. We're going to release it either late tonight or early tomorrow morning, and it will have your usual 2 weeks. And this homework will be all about starting. We'll cover things that we started today. We will start today, in fact, the mistake-bound model of learning and the perceptron algorithm. And it will have an experiment where you will implement the perceptron algorithm. I can assure you, if you thought decision trees was hard, this one's not going to be hard. It will be a lot easier because we will see the perceptron algorithm. It's literally like 5 lines of pseudocode, about 10 lines of real code. And I recommend that you spend some time designing that homework and making your homework pretty and all that, partly because this code will survive all the way to the end of the semester, because you will a code, for example, will basically be an edit distance of maybe 5 characters from perceptron. So you might want to plan ahead and not write this homework just for this one. And that also brings me to project. We're still hunting for a good task or an application for the competitive section of the project. That said, irrespective of which application we pick, it will have these following, these 3 characteristics. It will look like a Kaggle competition if you've seen one. If not, it doesn't matter. It will be bigger than your homework for sure, because it's more supposed to be more work. And in some sense, it will be the point of this competitive project is that you will get to try out different learning strategies. For example, if you've been careful with your ID3 code, you might have finished 1/6 of your project in terms of code, because you'll basically be doing what you just did on that data and submitting your results. If you feel like you want to try out a learning algorithm you've never seen in the class, or we have not touched in the class on this data, you're welcome to doing that. I insist that for this version of the project, you do at least, you try out rigorously at least 6 different learning algorithms. At this point, though, you don't have to worry about which learning algorithms or any such choices. All you need to tell me by Thursday is, are you going to do a regular project, which is 1 or 2 people in a group, or will you be doing a competitive project, which is by yourself? There will be a submission on Canvas that will let you submit this. We'll set it up most likely today or tomorrow. And the next milestone in the project part of the class will be a project proposal that you'll have to write, and it's due on September 29th, I think. You have to confirm the date on the lectures section of the class, on the class website. But I do believe it's due on the September 29th, and I've decided that until then, if you have decided to do a regular project beforehand, you still have the opportunity of switching to the competitive one. Okay? Any questions about this? Yes?
As far as, so our project needs to be bigger than our homework. What does bigger mean?
What does bigger mean? Bigger means it's more, the data set might be larger.
Is that like number of features?
Number of features and number of examples. Which means your code will take a little more time to run. In the data that we are trying to find, I'm hoping, in fact, I was hoping to announce the data set right now, but unfortunately I found out that it was 3.5 GB zipped. So that seems a little cruel. Mostly because you will end up killing one of the computers, and then I'll get angry emails. So I'm hoping to give you both featureized versions of the data and the raw data, so that you can use the features, but if you feel like you want to create your own features, then you can do that as well. And that might actually be the other way in which it will be bigger is it's not just one learning algorithm, but you'll have to try out a whole bunch of variants. It won't be guided the way your homework is. You are free to make your choices, and provided you justify them. Every choice that you make, you have to justify. It's bigger in the sense that it's closer to real life when you apply these things. So it will be more. I don't know necessarily the right answer, but there are many wrong answers. It involves a lot more exploration. Are there other questions about this? Yes.
So if you decide to do the competitive project, you do or don't need to do a project proposal then?
You do. In your project proposal, you'll have to tell me, it will be a much shorter project proposal. It will be like a little thing about what kinds of algorithms you plan to explore. And you don't have to stick by it, but at least give me some hint as to what you would like to do.
And that will help, we can do that better when we actually find out the data sets. So
yes, and I'm hoping to get that out to you by next week.
Okay.
Before the project proposal is due, I will have the data set.
I have one more question,
Okay.
sorry. And you said we had to do like 6 different learning algorithms?
At least.
Is that for both competitive and
No,
regular projects?
for the regular one, it's going to be closer to research like thing. You will be solving a problem. You'll have to define the problem. You'll have to find the data for it. You'll have to do the regular project will, if you're doing an experimental thing, or if it's a theory project, you just prove a theorem or things like that. The regular project is more open-ended. And it's suited for people who already have something going on and they want to inject machine learning into it, or who already have a strong opinion about something, or people who absolutely hate whatever data set I'm going to give for the competitive one. Alright. If there are no other questions, I think we should at some point start the class, so now is a good time. Today's class is going to take us on an interesting journey. We're going to touch upon this broad question for the first time of what does it mean to learn? And as I said in the beginning of the semester, we'll be asking this question again and again, and at least 3 times. And each way of answering this question will give rise to a family of learning algorithms. Today we'll look at one of those answers. It's called online learning. I am fairly certain we won't have time to start the perceptron algorithm today. My hope is at least I'll be able to describe online learning. So specifically, we'll be looking at the question of what does learning mean, and an answer which is online learning. And it turns out the perceptron algorithm is actually an instance of an online learner. It's a manifestation of this family of learning algorithms. And it comes with its own mistake bound and a bunch of variants, and it's an industrial strength algorithm that that's used widely even now. I mean, even in state-of-the-art work, so it's kind of a good bread and butter algorithm. So let's start with what does it mean to learn? Anyone can write down an algorithm. Anyone can write down code. Anyone can write down a heuristic, but it's not a real algorithm unless you can rigorously say something about it, unless you can quantify the performance, which means you have to define what does performance mean. What we really would like is we need to. You may have seen in previous classes the idea of space and time complexity. Space complexity is how much space does an algorithm take. Time complexity is how much time does an algorithm take to run. In learning, we have a third kind of complexity called sample complexity, and that is how many examples do you need, does the algorithm need, before you can say that the hypothesis that's been learned is good enough. Okay, and this is something that you may not have seen in other classes. Sample complexity is the currency that we'll be using to talk about learning algorithms. And it depends, the number of examples that you need depends on how you set up the learning game, how the learning protocol works. As an example, let's say that our function, the goal that the function that we would like to learn is a monotone conjunction. Monotone means there are no negations here, and it's a conjunction because these literals are connected by ands. So it's a x2 and x3. The function is true whenever x2 and x3 and x4 and x5 and x100 are true. Suppose in this situation there are 100 Boolean variables, but the learning algorithm, but only 5 of them are relevant, these 5. The rest of them, the function really doesn't care because it's not in the conjunction. But of course, the learning algorithm does not know the function and does not know that these 5 are relevant. Now let's try to analyze, in this specific case, how many examples are needed for a reasonable learning algorithm to find this function perfectly. The answer is it's not possible to answer this question completely until you also decide what's the learning protocol. How does the learner and the teacher or oracle or nature, how do they interact? And it's possible there are 3 possible kinds of protocols. Protocol 1 is when the teacher is available, the learner keeps asking questions, and by looking at the answers that the teacher gives, the learner internally reformulates the hypothesis. That's protocol 1. The second one is called teaching, where the teacher conveys the hypothesis somehow using only examples to the learner. In some sense, the teacher picks the right data set, perfect data set, and it's enough to completely convey the concept. The third one is actually more realistic. There is a random source, and it's exactly the thing that you guys have been working on. There's a random source of examples. You don't get to ask for more. If you choose, you can just ignore them, but you don't get to ask for more. And these examples come from the wild, and the nature or the teacher labels them using the true function. So the learner gets to see a random collection of labeled examples. Now let's see in these 3 protocols what the sample complexity might be. How many examples are needed to perfectly or to learn this function f. Let's consider protocol 1. This is where the learner proposes examples to the teacher and the teacher returns the labels. Let's step through an example. I'm going to convince you that this is, in this case, you don't need more than 100 examples. Suppose we know that we have the function, let's say the learner knows that there's a monotone conjunction. What the learner can do is ask, provide this example. All the features are 1 except for the last one. Remember that the function is a monotone conjunction, so you don't know what the conjunction is, but it has to be something x1 and x17 and x45 and so on. Now, let's say the learner gives this example. The teacher knows this function and applies this function to this example, and you see that x100, which is important, is 0. Which means the function value is 0. The function is false. This is proof that x100 is in the true function. Does that make sense? What then, after this, the learner will ask, is x99 then the next question is x99 in the conjunction? Question?
But this, isn't this like, so for this, if we follow this method, we need all 100 examples, right?
Sure, all 100, not 2 power 100. Right?
Also, this will not work if it's not a conjunction, if it was a
No, so the assumption is this example is only a proof of concept. We'll be looking at a couple of proof of concept cases today to understand the bigger point. But this is just a proof of concept. Yes, you're right. So the next point the next question that the learner will ask is x99n, at which point by basically turning off x99 and keeping everything on, and the function value is 1 even though x99 is off. That means x99 is irrelevant for the function. And you keep doing that for all of them. You do that for x2 and x1, and that's it. All you need is, as you said, 100 questions, and the learner will perfectly get the hidden conjunction. The hypothesis, I'll be using the symbol H to denote the learned function and F to denote the true function. And using these 100 questions, the learner is able to identify the conjunction. Is this clear? Is the protocol clear? Sometimes this is also called active learning, where the learning algorithm poses questions and nature labels them, or poses examples and the nature labels them. Active learning is is actually pretty good with sample complexity. You do not even though there are the input space, the set of possible examples has 2 power 100 examples. By carefully constructing the questions, the learner is able to learn the function using only 100. Okay. As an exercise, there's a question that says, what if I know that the function here is a conjunction but not monotone? I'm going to argue that a similar strategy will work, and I would like you to think about it later on when you go through this again. Okay? The second protocol is teaching. We will not see teaching at all in this class except from me. In this case, the teacher knows the true function and provides the training examples. What the teacher can do is, the teacher knows this function. So all it has to do is give an example where that contains a superset of these good variables that says that if x2, 3, 4, 5 and 100 are 1, then the output is 1. Then it needs to prove to the learner that every one of them is needed by turning off each of the required variables one by one and proving that the output is 0. So when x2 is 0 and 3, 4, 5 and 100 are 1, the output is 0. But when x2 is present, the output is 1. This means that x2 is needed. So this is like your logic puzzle with the kind of puzzles that you see in those old software coding interview questions, pirates and gold and such things. These are the kind of, it's basically just a puzzle. The learner has to convey, the teacher has to convey the function, and the teacher does so by providing the necessary and sufficient conditions. The first example says these 5 features are in the conjunction. The next 5 examples says if you take away any of these 5 features, the conjunction will turn off, the function will turn off, which means once you get these necessary and sufficient conditions with just 6 examples, the learner is able to learn the function. Exactly. So both with teaching and with in the teaching protocol and with this active protocol, which was the previous one, the learner is able to learn the function exactly with, in the first case 100, in the second case 6 examples. Before we move ahead, are there questions about this? Yes?
Are there any examples of when this would happen in real life, where we'd actually have a teacher?
Modeling teaching is very difficult. I have hardly ever seen these kinds of protocols ever being employed. On the other hand, the first one is definitely, it's widely used. It's called active learning. It's a huge area of research in itself. It also has interesting connections with HCI, because not only do you want to ask the question, you really don't want to present features like this. You want to ask the question. The teacher is usually a human, and then there's some sort of a interaction sort of a thing going on. So active learning is widely used. Teaching hardly ever, partly because modeling teaching is, when I say modeling, I mean studying teaching formally in anything that is not a toy is rather difficult. Yes?
How do you deduce, like, for example, that you need X2 from that?
From here?
Yeah.
Actually, you don't deduce it just from this. You look at this and this together. The first one says X2 and X3 and X4 and X5. So from the first one, what you can say is that the true function is X2 and X3 and X4 and X5 and X100. But it's possible that maybe X2 is not needed. This is not sufficient. This does not tell you that these are all needed. But by combining this with this, let's apply this function to this example. This gives you false. This tells you that by comparing this with this, with X, the only thing that's changed between those two examples is the value of X2. So when X2 is present, the function is on. When X2 is absent, the function is off. Which means X2 is needed. And the same thing applies from here to here. When X2 is present, the function, when X3 is present, the function is on. When X3 is absent, the function is off, which means X3 is needed. So by just looking at those pairs, the learner will know. Did you have a question? Okay. Alright, so let's move to the more realistic situation where a random source provides the training examples and the learner labels them. By the way, I should have mentioned this before, the notation I've been using is the thing within the parenthesis is the features, and the last element of that pair is the label. So nature provides some examples, it's just randomly sampled according to some underlying distribution. And I'm going to present a learning algorithm for this case. I'm going to call that learning algorithm elimination. What you will do is, you get a random training set, you throw out all examples that are labeled 0, that are labeled false. You look at only the positive examples, and the elimination algorithm will say, we'll take the intersection of all the features that are on. So X1 is on among all the positive examples. X2 is on among all the positive examples. 3, 4, 5 and 100 are on among all the positive examples, which means the true conjunction should contain a subset of these things. You basically, every positive example, so another way of, the reason this is called elimination is this example here eliminates X99 from being in the conjunction, because if X99 were in the conjunction, the label for that example would be 0. So the penultimate row there eliminates X99 from being in the hypothesis. The first row does not eliminate anything. The third row eliminates X6 and X99 and so on. Is the protocol clear? Is the learning algorithm clear? Is the elimination algorithm clear? Remember that we are making an assumption that the true function is a monotone conjunction. That's your hypothesis class here. And that is what lets you even build up this algorithm. Questions?
So would you then, so you take the intersection of all those, and then would you then verify that against all the false labeled ones?
It would work for the false labeled ones, right? It has to work for the false. Let's say that we take the intersection. Now, if assuming that the data is consistent, you will only make one kind of a mistake. Because this example is labeled true, definitely 2, 3, 4, 5 and 100 are present in that example. There may be other things, but definitely these 5 things are present. Now, because this example is labeled false, one of them must be absent. Right? So you will never eliminate any of the valid, that's a good question actually, because you will never eliminate any relevant feature using this algorithm. You're guaranteed that you only eliminate irrelevant features. So this algorithm will never make mistakes on the examples labeled false. Is that argument clear? Because I will be making this exact same argument maybe about a month from now on the same algorithm actually. So does that argument make sense? By taking the intersection of all the positive examples, of all the features in the positive examples, and creating a hypothesis of this kind, I claim that this hypothesis will never make a mistake on any of the negative examples that we never even looked at by the nature of this algorithm. Because if it was a negative example, for it to be negative, one of the relevant features must have been missing. So you can ask yourself, why is this example negative? Because x3 is missing. x3 would have never been missing in any of the positive examples. Why? Because you constructed it that, or rather, x3 cannot be missing in the positive examples because it's positive. And because you're only looking at the positive examples, x3 will never be missing in the hypothesis because you're making the intersection. So you'll never make mistakes on the negative examples. Okay? This is just an argument that x1 will be in the hypothesis. Whenever the true label is present, x1 is present, so x1 is in the hypothesis. Okay, but of course there's a problem here. In the first two protocols, we learned the function exactly. But here, there's this error. There's this x1 that's not in the true function. Is this good? Is this good enough? We've only learned an approximation of the true function. How do we know that this is okay?
I guess you could potentially calculate the maximum possible error. I mean, assuming that you could, that'd be one potential way we could look at it and see, if I am wrong, how many examples could I be wrong on?
Half of them, right? In this case, in the worst case. Half the examples will have x1 as present, because this is a Boolean. Let me ask you a question. Suppose nature created this training set for you by randomly sampling, examples, and it just so happened that in this really large training set, x1 was always present by chance when the label was true. If the process that created the training set had this property, maybe one could argue future examples will also have the same property. So maybe it won't hurt you too much because the future will be like the past. This is a kind of an assumption that we will have to make in one style of analysis. We never saw x1 equals 0 in the positive examples. Maybe we'll never see it in the future also. And so it's such a rare event that maybe it won't hurt us too much. Does that kind of reasoning make sense? The past is a good estimate of the future. So if we did okay on the training set, we should be okay on the future examples also. That's a style of analysis. And it won't be perfect, it will only be pretty good. Because we can't, look at the future for sure. This style of reasoning leads to what is called the PAC framework of learning, probably approximately correct learning. And we'll be looking at that probably in a month. But now, we'll look at a different style of reasoning, mistake-driven learning. One could argue that mistake-driven learning changes the game. It does not say what you will do in the future. It only says good is defined as how many mistakes have you made so far. All you care about is not making a mistake on the next example. And you keep track of the number of mistakes you've made so far. And if you can guarantee somehow that you will not make any more mistakes on the future, we are okay. And this also has a regularity assumption that the future will look like the past. If the examples keep coming from the same thing, from the same sort of distribution, you will not make many more mistakes because they look exactly like that. Does that make sense? So these are two different ways of analyzing or reasoning about the same thing. In fact, this sort of framework, in the first case also we'll have to put Bayesian learning right there, that the past looks like the future, and the future looks like the past, and so with high probability we'll not make mistakes in the future. But we'll be looking at mistake-driven learning right now. Mistake-driven learning is a subcategory of a family of algorithms that are called online learning. So let's just to kind of see where we are in the big picture. In the last lecture we saw linear models. Last two lectures we saw linear models for classification and regression. Today we started looking at this question of how good is a learning algorithm, and particularly we'll be looking at this idea called online learning, or more specifically mistake-driven learning. When linear models meet online learning, you get algorithms like the perceptron and the Winnow algorithm. We'll look at perceptron in the next lecture and the Winnow algorithm next week. This is not the only way of answering this question. There are other ways, and that's the rest of the semester. If you look at another framework called PAC, you'll get support vector machines. If you look at Bayesian learning, you'll get logistic regression. End of the day, we are always asking the same question. How do I know that my learning algorithm is good? And just answering the question in different ways naturally gives rise to different learning algorithms. So is the big picture clear? I mean, this is just a map of where we are in the big scheme of things. Does that make sense? Any questions about, does anyone have violent disagreements about this? Or not so violent, maybe preferable. Okay, let's look at online learning. As I said, you'll be looking at two new learning algorithms in this under this framework, the perceptron and the Winnow. And the reason we'll be going through some amount of depth with respect to the perceptron and both these algorithms actually. And part of the reason is, in online learning, the algorithms themselves are very simple. They are. I'll give you the general sketch of the online learning algorithms in a bit, but the algorithms themselves are very simple. They lend themselves to sometimes fairly simple analysis. I'll be walking you through the proofs in the class. And perceptron in particular has very intriguing connections to the stochastic gradient descent algorithm that we saw last week. So it turns out it has there's a way of thinking of perceptron as an instance of stochastic gradient descent as well. Across all these things, I want you to watch out for the following issues. The importance of representation. And hopefully by the end of today's lecture, I'll get to a point where I'll point out that even though we're talking about all these Boolean functions and all these things, it is so much easier just to have learning algorithms for linear classifiers, because they subsume all these things and they also have some interesting properties from the complexity point of view. And that's the other aspect, how the complexity of learning. And typically when I say complexity of learning, I will mean sample complexity. How many examples do you need before we are good enough? And I'll define good enough formally in a bit. Much later on we'll see kernel-based methods. I'm just throwing this in here right now because when you review these slides at the end of the semester, this will make sense. It's possible to have nonlinear classifiers as well. And we'll be looking at the importance of features and how a change of features might actually make a difference. In particular by looking at the XOR function that we saw last week. But let's set up the game here. Suppose we live in this situation where the learning problem, the proof function, is an extremely high dimensional function. Namely, you have a huge number of features. The number of features that you have might be in the millions. And this is not uncommon, particularly in applications like, say, natural language processing, where a reasonable learning situation might involve like 1 million features. Suppose you also assume that even though there are 1 million features, the true function is actually dependent on a very small set of them. In this case, the true function is only dependent on 5 of them, even though there are 1 million features. But you don't know that upfront. And this may seem like a ridiculous situation, but here's an example of a task that introduced me to this idea and hopefully shed some light. There's a mistake in this sentence. This word here should not be desert, it should be deserts. But a spell check system will not find this because there's no typo here. There should be an extra S here. But the way, if this seems confusing, I assure you this is a mistake. But the point is, it's not trivial to find the answer to this by just having a list of correct words and saying, this word is not in the dictionary, because both deserts and deserts are in the dictionary. And one way to get around this is to train a classifier. The classifier looks at this word here and gets some features from nearby. What's the previous word? What's the word 2 before? What's the word after? What's the word 2 after? And you train a classifier, and that classifier is going to be extremely sparse because this feature space is going to be the size of the English dictionary. But the number of relevant features for this concept, deserts versus deserts, is going to be very small. Middle Eastern, deserts. Well, you want to pick deserts because the word sweetness shows up. On the other hand, if it was Middle Eastern, deserts are known for their vastness. That's the desert with sand. This one is the desert with sugar. This is an example of actually a real task called context-sensitive spelling correction, where you use the context to decide whether you've made a mistake in the spelling or not. And this has this property where the dimensionality is extremely large, but the number of attributes that are relevant is small. So the question that shows up, that becomes interesting here is, can we develop learning algorithms that only depends weakly on the dimensionality, because the dimensionality is very large. We want the learning algorithm to depend more on the number of relevant features. And when I say depend, I mean the number of examples that are needed. Sample complexity of this learning algorithm should depend only weakly on the underlying dimensionality. Of course, there's the question of how should we represent the hypothesis, but I'm not going to answer that at this point. Under this situation, let me define a class of algorithms that are called mistake-bound algorithms. Suppose you have an instance space where the examples are vectors in n dimensions. And suppose the true function is a concept class, the true function is in the concept class C, and the size of the concept class, the number of functions there are, is parameterized by this n, is some function of n. Oh, by the way, do feel free to interrupt me or stop me from going ahead if you feel that this is not clear, I enjoy questions, and somehow I feel like this is too early for you to be asking questions, but feel free to do that. And the way we set up learning in this situation is, this is the general recipe for an online learner. The learner sees an example. It makes a prediction, h of x, it has a hypothesis, it makes a prediction, and after making the prediction, the true label is revealed to the learner. So online learning can be seen as this kind of a two-player game between the learner and nature. The learner sees an example, and it makes a prediction, and then in the very general case, it can either be the true label can be revealed to it, or even without revealing the true label, the learner just suffers what is called regret for making that prediction. If regret is 0, then there's no regret. You laugh, but that's the technical term. The learner makes a prediction and then suffers immediate regret for the prediction.
Does it apologize?
It apologizes by correcting itself. So online learning is this kind of a game that goes in rounds. And we need to define performance of the hypothesis, and what we'll say is that the learner makes a mistake if the true label does not match the prediction. Seems totally reasonable. Now, I'm going to just introduce the idea of a mistake-bound algorithm. Suppose for a fixed target function, suppose we have a fixed target function, and suppose we have a fixed algorithm A. Okay? And suppose we have a fixed sequence of examples. So we are fixing three things here. We are fixing the target function, we are fixing the sequence of examples, and we are fixing the learning algorithm. Which means everything is fixed, because now we can just let the learning algorithm proceed in these rounds and count the number of mistakes. Let's call that MA of S. Now, notice that this is a property of the algorithm, the function, and the sequence of examples that have been chosen. The function is inside a concept class C. Now, I can ask, what about the adversarial situation? What if you pick the worst possible function inside this target class, you pick the absolute worst function from the learning point of view, you pick the worst possible sequence of examples, and count the number of examples, mistakes made by this algorithm. Does that make sense? For a concept class, we are fixing the algorithm. For a concept class, we find the absolute worst function to learn, F. We find the absolute worst sequence of examples for this function. In a way, we are trying to confuse the learner as much as possible. We are trying to not be nature, let's say, is being adversarial and is trying to force the learner into making as many mistakes as possible. This is a property of the concept class. We find max is just giving us the worst function and the worst sequence. For the worst function and the worst sequence, what's the number of mistakes made by this algorithm? Let's call that MA of C. Are these two notations, do they make sense? Now, I can say that the algorithm A, so the MA of C is just a property of the algorithm and the concept class, right? There's nothing else. There are nothing else involved in the definition. This algorithm A is called a mistake-bound algorithm if this, for this concept class, if the number of mistakes it makes for the worst possible function, for the worst possible sequence, is polynomial in the dimensionality, in the input dimensionality. By that I mean, polynomial is a theory person's way of saying it's small. It could be n power a million, but it's still small. It's not exponential. So let me just walk you through this again. For a particular, let's say we have a function that is coming from a concept class. Let's say we have a sequence of examples for that function. And let's say we have a learning algorithm. In all of this, I'll be using A as the learning algorithm and C as the concept class. So we are asking, how good is this learning algorithm? So for a particular function from the concept class, for a particular sequence of examples, for this that is fixed, we count the number of examples, mistakes that the algorithm makes. And now we let nature pick the function and the sequence of examples that forces our algorithm to make as many mistakes as possible. The maximum number of mistakes that can be possibly made for any function in the concept class, for any sequence of examples, for the most adversarial sequence of examples if you want, suppose that number is still only a polynomial in the input dimensionality. Then we call this algorithm a mistake bound algorithm. Questions about the definition? Yes?
So for, I guess as you're defining n, so n is, when we say n, the dimensionality, that's the number of features. It doesn't really particularly care how many examples there would be for this feature, like say...
Adversarial, worst case.
I was just saying, like, because if it had, I just remembered from my flexible class, with the number, if you look at a number as the number of bits, that's going to give you different complexity analysis than if you treat it as the actual number in your complexity.
Those are like minor, polynomial variations, so that doesn't matter often. What we really would care about is the dimensionality of the input. That's it. That's a representation question, and the n is the dimensionality of is the number of features that are used by the learning that exist in the problem in some representation. Other questions about just the definition? Notice I have not proved anything here. All I am telling you here is if such a property holds, then the algorithm is called a mistake bound algorithm. There's nothing more here. I'm just saying that this is a definition. I've not even told you, it's possible that there does not exist any algorithm in the universe that has this property. We still don't know. I've just defined a set of algorithms for concept classes. In fact, this is by the way not the most generic setting. There are more complex ways of defining online algorithms. The most popular one actually is based on something called minimizing regret. You don't want to minimize the number of mistakes, you want to minimize a generalization of this called regret. We won't be talking about this regret bound algorithms in this class, partly because the analysis gets just a bit more complicated, and sadly we don't have time for that. But this should kind of give you the the necessary background if you want to go and read about regret bound algorithms. So let me just point out a few interesting things about online learning. Notice that it makes no distribution about it makes no assumption about the distribution of the examples. It's possible that there's an adversary, or it's possible that the teacher or nature is being adversarial. And in fact, the definition is adversarial. Right? You're looking for you're trying to find a situation where where nature is actively trying to confuse the learner. But the protocol itself is very simple. The protocol itself proceeds in rounds. The learner gets an unlabeled example, it makes a prediction, and then the true label is revealed, and possibly the learner corrects himself. That's all that happens. It's a game, right? It's a two-player game where the learner makes a move. An example is revealed. The first move is made by the learner, and that move is the prediction, h of x. The second move is made by nature, and that's the true label, f of x. And if f of x and h of x are the same, the learner wins that round. If f of x and h of x are different, nature wins the round. Right? And nature's goal is to confuse the learner. So nature is allowed to pick examples. So it picks examples that are adversarial, that tries to force the learner into making mistakes. So the way we are going to define good in terms of is this good enough is if the learner stops making mistakes, or We count the number of mistakes and we say that this is the limit on the number of mistakes. Oh, by the way, what we have here is a property of the learner, of the learning algorithm, right? The learning algorithm is called a mistake bound algorithm if it makes only a polynomial number of mistakes in the most adversarial situation. The concept class itself is said to be learnable in the mistake bound model if there is a learning algorithm that has this property. Maybe we don't know that learning algorithm. Maybe we can just prove that there is a learning algorithm, but I don't know what it is. But if I can prove that there is a learning algorithm for a concept class, then the concept class is said to be mistake bound or learnable in the mistake bound. So far, all I have done is 3 definitions. 1, I have defined this online learning game with a mistake bound model. 2, I have defined what is a mistake bound algorithm, and it is simply an algorithm that makes a polynomial number of mistakes. 3, I have defined what it means for a concept to be learnable in the mistake bound model, which is just if there exists a mistake bound algorithm for that concept. I've just given you 3 definitions. It turns out these definitions are actually not unreasonable. It has 2 good properties. 1, the game itself is very simple. It proceeds in rounds. There's like not much going on. There aren't too many moving parts here, and yet it's actually widely applicable. Online learning, for example, is a good way of modeling, how a child might learn a language. It is used widely in robotics. In fact, reinforcement learning can be seen as a generalization of the situation. It's also important in particularly increasingly common case where the data sets are so large that they can't even fit in your memory. Or maybe you want the learning algorithm to run in one of these devices, so you can't even load the data set in your phones or in your tablets. And the other thing I wanted to mention is I want you to think about we are counting mistakes here, right? We are counting the number of mistakes that the learner makes as it goes along. How does this connect to the real goal of learning? In other words, the real goal being, I want a hypothesis that does well on previously unseen data. Does this capture the real goal? Is it enough to stop making mistakes? If I can prove to you that after seeing a certain number of examples, this learner will never make any more mistakes in the future, would you call that success? Seems like it's okay, right? If I can prove to you that it will never make mistakes, that means it will do perfectly on previously unseen data. And by the way, this seems like an outrageous claim. To say that it will never make mistakes is a rather bold claim, because you have not even seen all the examples. And yet if you're able to prove that a certain learning algorithm will never make mistakes, it seems like it's a property that should not seem natural to you. It's something that should seem rather made up. How could that happen? How could you possibly make such a claim that such an algorithm can exist? I'll actually prove, and in fact that should be your first question. Yeah, sure, this guy's defined a class of algorithms, maybe that cannot happen. Hopefully in another maybe 5 minutes, I'll prove to you that such an algorithm can exist, and I'll prove it by construction. It's a worst case situation. There's no notion of distributions. It does not need any memory, because all you do is you get an example, you make your correction, you make a prediction and correction, and throw it away. You don't need to remember any examples. All you need to do is, the only memory you need is for that one example that you're currently processing and your hypothesis. The disadvantage of this is it's actually too simple. It's not clear when the mistakes will happen. If I tell you that this algorithm will make only 3 mistakes in its life, maybe that's good enough, maybe it's not. Maybe it's not good enough, because it's possible that those 3 mistakes are going to happen when you really don't want them to happen. So imagine a self-driving car, and I tell you that I'm going to give you a self-driving car, but it will kill exactly one person and no more than that. Probably not the best thing. So it's not clear when the global behavior of the algorithm is not clear. On the other hand, the advantage is that it's simple, which means it lets us analyze this thing quite quite easily. And even in this simple setting, we will run into problems, which is good. I mean, problems are good. We will run into situations that manifest themselves even in the more complex things. And there exist family of generic conversion techniques that take online algorithms to other kinds of guarantees. You know, the pack model that I was telling you about, you can convert from online to what are called batch. And if you are interested in looking this up, the keyword is online to batch conversion. I'm not going to talk about it, but we'll see an example of this later. Another thing I want you to think about is counting mistakes good enough? Now, we don't care about, the true function itself. We really don't care about the function. We don't care about the hypothesis. All we want is some black box that stops making mistakes. Now, here's a mistake-bound situation. Suppose the learning algorithm, it just so happens, is presented with the same example again and again and again, and it just remembers the label. Under the mistake-bound model, it's fine, because it remembers the label, it sees the same example again, it's not going to make a mistake. It sees the same example again, it's not going to make a mistake. And this keeps going on, and this is okay. Because if we're not going to learn the function because we are only seeing that one example again and again, but we are not going to make any more mistakes. So under the mistake-bound model, this is okay. But if your goal is to learn the function, it's not, because you've only seen one example. It just so happens that that example keeps coming again and again. Is the distinction clear? Does that make sense? On one hand, you want to learn a function. But here, what we are measuring is the number of mistakes. You cannot possibly learn the function using only one example, but if it just so happens that nature is not adversarial, but only keeps sending you that one example again and again, you're not going to learn the function, but you're not going to make any more mistakes either. So this is a example where mistake-bound model says this learning algorithm is okay, but if you care about the true function, you're not okay. So, as I said earlier, it's not clear that mistake-bound algorithms should even exist. I have just defined a set of algorithms and given them a name, but doesn't mean that that set should have any algorithms. And as a proof of concept, I'm going to show to you that there is an algorithm that's called the halving algorithm, which is actually impractical from a real-life point of view, but it is a mistake-bound algorithm. I'll set things up for the halving algorithm, but I won't be able to get to all of it, but we'll pick up from there. So, let's say we have a finite concept class, and the key word here is finite. Let's say we have a finite concept class, we have only a fixed set of functions. Our goal is to learn a function from that set. And I'm going to define this algorithm called con. Con stands for consistent. And this algorithm proceeds in rounds. Remember, it's an online learning algorithm, so we proceed in rounds. When a new example comes in, what you do is at any point you maintain a collection of concepts. So you start off with a concept class C. A new example comes in, let's say you have functions inside this, and let's say there is some hypothesis here. This is a set of functions. A new example comes in, and what you do is you randomly pick a function from this set, make a prediction. And let's say you made a mistake. Then what you do is you drop all functions inside this set that also make mistakes. So let's say H1, H2. You predict using h of x, and you take the subset of all these examples, let's say, that do not make mistakes on this example. So what you do is, at any point, you only keep those functions that are consistent with all your examples so far. That's why it's called the consistent or con. So when a new example comes in, you randomly pick another function from this, and let's say it makes a mistake, you take a subset. You keep doing this again and again. Is the game clear? Is the protocol, does that make sense? So you, instead of maintaining a function, you maintain the entire set of function at any point to make a prediction. So for an online learner, you need to somehow make a prediction, and here to make a prediction, what you will do is draw a random function, you don't care which one, make a prediction. If that function has made a mistake, then you drop all functions that are inconsistent, otherwise you move to the next round. Clearly at any point, at any point, Ci plus 1, the set of functions that are consistent with examples so far, at the I plus 1 step, is going to be a subset of the set of, subset, not a strict one, of the set of functions in the previous round. Because you're only dropping functions that you may be either dropping functions or you'll keep the same thing. So the size of Ci plus 1 is less than the size of Ci, which means you're getting closer and closer, you're zeroing in on the true function. Now, which means there are only, this is a finite concept class, so the number of mistakes that you can possibly make is the total number of functions minus 1, because there is, suppose you have one consistent function. And the question that we'll get to in the next class is, can we do any better? But before we wind up, are there questions about this algorithm? Yes?
So if you only pick like one to evaluate the existing one, how do you know like the subset to drop without evaluating all?
You have to evaluate all of them. But you choose whether to drop or not using that one. If it so happens that at that point you luckily picked a good function, you do not drop.
Any of them?
Any of them.
Okay.
Either you, exactly, that's right.
Okay.
You could have variants by saying that at every point you evaluate every function, but this is mostly to, let's say, for efficiency. But this is a hypothetical algorithm. I would not want any of you to be implementing these, because you know as well as I do that if you have a Boolean concept class, the number of functions is 2 power n. So you should not be implementing these things, but as a conceptual object, this it's only finite, the number of functions. Any other questions about this algorithm? Alright, I can see that many of you are eager to get back to your homework, so I'll stop a whole minute early, and we'll pick up from here in the next class, and I'll prove to you that mistake-bound algorithms exist. Oh, and I have office hours right now. As we move into my office and